Welcome, everyone. It is a great pleasure to introduce someone who needs no introduction. Michael Farber is coming from Queen Mary University of London to tell us about the topological complexity of spherical bundles. Please, Michael, go ahead.
Thank you, Jesus, for a very nice introduction. Thank you. I'm pleased to be here to give a talk at the seminar, and thanks for Jesus and John and Dan for inviting me. So I want to start with a general broad view on the subject. It is always helpful to remember why are we studying this or that specific mathematical problem and where our progress can be applied. Oh, sorry, 1 second. Doesn't. I cannot. I don't know what's wrong here.
We can hear you.
Yeah, but I want to change my slide. No, and I cannot get out of this mode.
Maybe your internet connection.
Yeah. Now it's good.
Okay.
Good. Okay. So this problem, which will be focus of this of my talk, and which is actually part of in the discussion of this seminar, all these problems are at the heart of the mathematical foundations of AI. Alan Turing in 1950, in his famous paper, he studied this question: what is machine intelligence? How to define machine intelligence, how to detect machine intelligence, which now we call it AI. And Turing suggested a test, which he calls the imitation game, where a judge asks questions trying to decide whether he deals with a machine or with a human. And if the judge fails, this means that this machine possesses the intelligence of human. So, I mean, it's a very well-known movie. I'm sure people are familiar with this. So we can say that in some sense, AI is equivalent to the ability of a machine of automated decision-making. And in our life, we make many decisions. So human life is a sequence of decisions. And eventually what we decide in the duration of our life determines what we are. Mathematically, decision is a choice. And there are two classes of choices, discrete or continuous. So discrete choices are when we have to make a choice out of finite set. And examples are left or right, buy or sell, red or green, and so on. But in this talk, well, in this topic, which we discuss in the seminar, an algorithm or a machine has to make a choice out of continuum possibilities. And this picture illustrates the situation. So we have a robot which is at certain position, and it needs to get to some other position, desired state, and there are obstacles on the way. So the robot must make a choice and select its trajectory. And this is what in robotics people call motion planning algorithm. So this is what we will discuss in this talk. I'll just start with kind of material which I'm sure people know, but maybe not 100% of participants know this. And besides, I will use similar techniques in my more advanced part of my talk. So we make the following kind of translation of the motion planning problem into a mathematical problem. So we associate with the system its configuration space. So a state of the system can be characterized by certain number of numerical parameters, x1, xn, which could be some lengths or angles. And therefore, a state of the system can be viewed as a point in some Euclidean space. And the variety of all states is a subspace of Euclidean space. So it has natural topology. And we can translate many questions from robotics into topology using this dictionary. So system, for us, it will be the topological space, which represents the configuration space of the system. Points of this space are states of our system, and motions of the system are represented by continuous curves in this space. So motion planning algorithm can be defined as follows. So if we have a space X, as we agreed, space for us is a space of states of a system. So a motion planning algorithm associates with every pair of states a motion of the system, a path in this space, which starts at first point and ends at the second point. So this motion planning algorithm is a map from x cross x to x to the I. And this map should be such that if you compose it with the standard map from x to the I to x cross x, so this composition should be the identity. Okay. So in other terms, we can say that this motion planning algorithm is a section of this path vibration. And there is a lemma saying that a section of this vibration exists if and only if our configuration space is constructible. And this is an example of convex configuration space, which is constructible. And here we can have very simple motion, straight line motion, which is continuous. So, but in general, configuration spaces are not constructible. Therefore, there is no globally defined continuous motion planning algorithm. And therefore, we come to this notion of topological complexity, which is as follows. So we start with a path-connected topological space, and we look at the minimal k, minimal integer, such that x cross x can be covered by k plus 1 open sets, u0, u1, uk, with the property that there exists a continuous section Si over each ui. And the facts which we know about this number TCX, or topological complexity of X, that it is a homotopy invariant of X, and it is zero if and only if the space is constructible. So, and this is a kind of first example. If we look at a sphere, Sn, topological complexity of a sphere is 1 when n is odd, and 2 when n is even. And the kind of the proof is that we can always take as F0 the set of pairs which are not antipodal. And then here we have a continuous section when A moves towards B via the geodesic arc. And then second set, F1, consisting of the antipodal pairs. So here we can have a section only when n is odd. In this case, we can use tangent vector field to the sphere and move along this tangent vector field from point A to point B. Okay, but if n is even, if the dimension of the sphere is even, there is no such vector field. So there is an extra set, F2. I will not go into details. It is kind of known, it's all stuff. But I just want to emphasize that this example of TC of spheres is relevant to my talk. I just wanted to say that many important mathematical results concerning topological complexity of motion planning were obtained by Sasha Dranishnikov, Jesus Gonzalez, Mark Grant, Jon April, Peter Landweber, Lucille van den Broek, and many other people. So now I want to start with a new notion of parametrized topological complexity. It's relatively new because it was published in last year in a paper with Dan Cohen and Shmuel Weinberger. So the purpose of this parametrized motion planning is that we want to have the motion planning algorithms flexible and universal. So they will not depend on specific external conditions. In fact, external conditions are viewed as part of the input of the algorithm. So the input of a parametrized motion planning algorithm contains the current state, the desired state, as well as the state of the external conditions. So in this way, it is slightly different view on the problem. Topologically, it's very different view. And let's see in more detail. So in more detail, we can say that we have we can consider a map P from E to B. We will assume that it is a fibration. However, in some applications, it may not be a fibration, but for my talk, and I mean, it will be easier to view it as a fibration. So the points of B parameterize the external conditions. And once you specify the point of the base, the fiber of this fibration XB, or the fiber over B, is the configuration space of the system constrained by the external conditions B. So in this setting, we don't have a specific configuration space. We have a variety or bundle of configuration spaces. And we want to have an algorithm which will work for all these bundles, for all these fibers. So let me, here is an example, which was actually our main motivation for this, to introduce this notion. So let's look at configuration space of n plus m particles in RD, and we will project it onto the space of m particles in RD. This is known as the Fadel-Norwitt vibration. So here, the first n particles will represent positions of the robots, and the last m particles, O1 or m, represent positions of the obstacles. So we all these points must be mutually pairwise distinct, and projection is when we project this configuration onto only to obstacles which we view as external conditions. So the fiber is a configuration space of n points in the complement of the obstacles. But in this setting, obstacles are not fixed. So the algorithm should be able to work for any position, for any configuration of the obstacles. So what kind of algorithm in this specific case do we expect? So the algorithm will take as input two Z1, Zn, these are current positions of the robots, and then Z1 prime, Zn prime, these are desired positions of the robots, and also O1, Om, these are positions of the obstacles, and obstacles shouldn't be moved. I mean, obstacles are fixed. So output of this algorithm will consist of continuous coordinated motion of the robots, Z1t, Znt, from the initial to the desired positions, avoiding collisions with the obstacles and with other robots. So if we translate this into general setting, we can say that, okay, so we have a vibration P from E to B, and then we consider pairs of points in E or in the fiber, in the total space, which lie in the same fiber, so they live under the identical external conditions. And we also look at a space which we denote by EIB. It is a space of continuous path gamma from I to E, such that their projection into the base is constant. So these are paths lying in a single fiber. These are motions of the system under fixed external conditions. Okay, so these are notations. So we have two spaces associated with the initial vibration. So first space is denoted by E2B, and the other space is EIB. And there is a map, which is called pi, capital Pi here. This map pi goes from EIB to E2B. So it associates with every path gamma the endpoints, the initial point and the final point of this path. So, and now this main definition, a parametrized motion planning algorithm is a section of this pi, of this vibration pi. In fact, pi is a vibration. It is a separate statement, but I will not focus on it. So I just repeat, a parametrized motion planning algorithm is a map A, which goes from E to B to EIB, such that if you compose it with pi, it will be the identity. Okay. By the way, if there are questions, I'm okay with interrupting me. Okay, so this was a definition of what is a parametrized motion planning algorithm, and now related notion of parametrized topological complexity. So parametrized topological complexity is denoted by TC of this vibration, is defined as a sectional category of this vibration pi. So it is actually complexity of any section or any parametrized motion planning algorithm for this situation. So specifically, this TC of pi of P from E to B, this topological complexity of vibration is the smallest integer k such that E to B admits an open cover where each set UI has a continuous section of pi. And using a recent result, very useful result of Jose Garcia Calcines, one can show that if P is a locally trivial vibration and the spaces are metrizable, separable ANRs, which is always true, well, in real life, it's always true, then instead of open covers, one may use arbitrary, sorry, I made it twice, arbitrary partitions. So instead of open covers, we can just partition our base, which is E to B, with such that each of these sets admits a continuous section. Okay, so this now a few properties. So the first property says that if the bundle is trivial, then this parametrized TC equals the usual TC of the fiber. So in this case, it's obvious that so in this case, we have kind of stationary configuration space, and there is no need to introduce parameterization. It will be, this parameterized TC will be equal the usual TC. So this is clear. The second example is that if we have a principal bundle with fiber, a connected topological group G, then TC, this parameterized TC is again the same as the usual TC of the fiber, which is actually the same as the category of the fiber. So again, in this case, there is nothing new, on top of this, what we knew before. And in general, this parameterized TC is can be only bigger than the usual TC of the fiber, but it can be just equal to it in these examples which we just discussed before. Okay, but in fact, I mean, many examples which we will discuss later in this talk show that actually parameterized TC can be arbitrarily larger than the usual TC. So first properties, property 4, which is quite useful, it says that this parameterized TC is 0 if and only if the fiber is contractible. And there is an upper bound in terms of the dimensions of the fiber and the base and connectivity of the fiber, which is number 5 here, statement number 5. It is an upper bound for parameterized TC. And then there is a lower bound. So lower bound is important, and I'll just go through it. So so we look at diagonal map delta going from E to E to B. So this map maps point E into the pair EE. And we can look at the induced map on the cohomology delta star. So this map goes from cohomology of E to B to cohomology of E. And then the statement is that this parameterized TC is greater than or equal to the couplings of the kernel of this delta star. Okay, so this is lower bound. So in some cases, by combining lower bounds and upper bounds, you can find the answer. And this actually happened in this paper, which a joint paper with Dan Cohen and Shmuel Weinberger. So in this paper, we looked at this parametrized TC of Adele-Neuwirth vibration. In the case when dimension of the space D is odd, and we showed that this parametrized TC equals 2n plus m minus 1. So in this case, we see that parametrized TC is higher than TC of the fiber, because m, because of this fact, summoned m, the TC of the fiber will be without m. And then in the case when D is dimension is even, then parametrized TC is one lower. It is 2n plus m minus 2, and it was proven in the paper which is mentioned here. This paper will appear in the journal which is called Annals of Mathematics and Artificial Intelligence. And alternative proof of the theorem of this theorem for even D, actually for D equals 2, was suggested by Mark Grant. Very interesting proof using completely different techniques. And his preprint is here. So in this preprint, which is on top of this slide, joined with Shmuel Weinberger, we have a very explicit parametrized motion planning algorithm for even and odd dimensions. The number of the complexity is exactly this optimal number. However, each of these domains is a union of many connected components. And one of these domains has n plus m factorial square divided by m factorial connected components, which is a huge number. Even in the case of 5 robots and 3 obstacles, it is 270 million domains. And on each of these domains, we have a different algorithm, different function. So, I mean, real complexity is much higher. I mean, but we are dealing with topological complexity only, which is smaller. So I just wanted to emphasize this point, that it would be interesting to understand what is actually real complexity for this problem. And this number, this 270 million, is real, I think. You cannot avoid this. Okay. So, okay, so now I exactly start the new topic. The topic of my talk, topological complexity of sphere bundles. So what I was speaking until now was an introduction. We consider a rank Q vector bundle from E to B. So it's kind of parameter, and we take only unit sphere bundle out of it. So we assume that each of such bundle has a metric structure. So there is a positive definite scalar product on each fiber. So we can take the set of unit vectors. They form a bundle. The fiber of this bundle is a sphere of dimension Q minus 1. So this spherical bundle is, we can think of it as parametrized spheres. So it is a parametrized sphere, kind of twisted sphere. And the question is, what is parametrized TC of this parametrized spheres? So, I mean, starting this, we have to remember that TC of the usual sphere, non-parametrized, we just mentioned, I mentioned earlier, it is 1 or 2, depending on the dimension is odd or even. So let's see what happens here. So before I start with TC of spherical bundle, I want to remind you a statement from the work of Schwarz about sectional category of a spherical bundle. Schwarz didn't use term sectional category, he used the term genus. But I know that people in this seminar already accustomed to use sectional category, so I also follow this tradition. So suppose we have, I just start this lemma of Schwarz. So we start with the oriented vector bundle of rank Q, and then sectional category of this unit sphere bundle. So I use this notation. Dot means that I look at unit sphere bundle. Psi dot is a projection of the unit sphere bundle. So the sectional category of unit sphere bundle is greater or equal than the height of the Euler class, which I will describe just in a few on the next slide. And if dimension of the base is less than something, then the sectional category equals the height of the Euler class. So this Euler class I denote by E of psi, and it is integer class with of the degree Q. And height means that we take the largest integer, largest power of this class, which is non-zero. So just to remind you properties of the Euler class of oriented sphere bundle. So first property, the major property, is that it is a first abstraction for a section of this fibration. So it is zero if our fibration has a section. And the kernel of the induced homomorphism, this homomorphism we always use to estimate sectional category, induced homomorphism from cohomology of the base to the cohomology of the total space. So this kernel is a principal ideal generated by the Euler class. And this is actually part of this Giesian sequence, Giesian exact sequence. And number three, if this Euler class is zero, then the bundle admits a cohomological extension of the fiber. It means that it satisfies the Lorentz theorem, and in that case, the total cohomology of the total space is the product, tensor product of cohomology of the fiber and cohomology of the base as abelian groups. Okay, so this was just to remind you about Euler class, and now we don't know, maybe we don't need, but I just want to again come back to this lemma of Schwarz, that sectional category of spherical bundle has as a lower bound height of the Euler class, the height of the Euler class. Okay, now we start the main topic, TC of a sphere bundle. So this is what we want to understand. Okay, so let psi be an oriented round Q vector bundle, and psi dot is its unit sphere bundle. Now we look at double dot, E double dot. So it is a space of pairs of unit vectors lying in the same fiber and mutually orthogonal. So it's probably has a name like Stiefel, I don't know, Stiefel manifold of this bundle. But I mean, it's kind of Stiefel version of this initial bundle. So these are pairs of orthogonal vectors lying in the same fiber. And there is a projection which I call psi double dot. It's projection onto the first vector. And this projection is a sphere bundle with a fiber sphere of dimension q minus 2. So one lower, dimension one lower. And it has also Euler class, E psi double dot, which is a class in of degree q minus 1 with integer coefficients. So I'm skipping integer coefficients. But if it's not integer coefficients, I will emphasize that. So the main result is that this parametrized TC of unit sphere bundle has as upper bound sectional category of this Xi double dot plus 1, and as a lower bound, it has height of the Euler class of Xi double dot plus 1. Okay. All right. So now the upper bound is very simple, and I will describe it. So let's think about the upper bound. So the upper bound, first we take a subset U of pairs of vectors x, y in the same fiber, which are not antipodal. Over this set U, we have a continuous section. So I mean, it's just written explicit formula, but it's you just move from x to y along straight line, and then project this line onto the sphere. So normalize, kind of divide by the norm, and this norm never zero because this x and y are not antipodal. So this is fine, and we have a section over this set U. So what remains is the set of pairs with antipodal x and y, which x equals minus y. So now we want to deal with this space, x and y, which are antipodal. And we denote by P1 the projection from on the first vector. P1 is the projection on x. Okay. So now, okay. So suppose I have a subset A of E dot. So E dot, remember, E dot is the space of unit vectors of the original bundle. Suppose I have a kind of set of space of unit vectors, and on this set, I have a section, let's call it SA, of Xi double dot. So what what does it mean actually? It means that for every unit vector of A, I can continuously assign a vector, unit vector, which is perpendicular to this vector. Okay, so now if we have such situation, if we had such A and a section, then we can define a section of this pi as follows. So we take pairs P minus 1 of A. So these are pairs where the first vector belongs to A. And so we move from A to minus A, as it shows on this picture, along half a circle. And this half a circle, this in the direction pointed by SA of X. So this section of this double dot bundle shows us how to move from X to minus X. So this gives a section which I call S prime A. Okay. And now if K is the sectional category of this Xi double dot, And if we have a partition or covering of E dot by the sets A0, A1, AK, and sections SAI of this E double dot vibration, then V, the total space, is covered by pre-images of the sets, and on each of the sets we have a continuous section of pi, and this shows that TC of parametrized TC of spherical bundle is less or equal than this K plus 1, which corresponds to this pairs of not antipodal vectors. So it is sectional category of Xi double dot plus 1. So this is the upper bound. Are there any questions?
Hi,
Yeah.
yes. Did you use reduced sectional category to define the parameterized complexity?
Yes, it is reduced. I mean, it is.
Well, no, it seems like the number is off by 1 then.
Yes, it is. It is here. You can see it starts from 0. Counting starts from 0. It is reduced.
Okay.
So what?
Back on this slide, you have it as reduced, but you still put it as less than or equal to K plus 1 rather than K. Am I missing something?
No, you're right. This
Okay,
one comes from this set of, sorry, remember we started with this U pairs which are not antipodal.
Oh, okay, my bad, thank you.
So this one comes from this U.
Sorry about that.
Is it okay?
Yep.
Okay. All right, so now the lower bound. Okay, so I mean, we need to remember the general kind of cohomological lower bound. So we need to consider the diagonal map delta, which goes from E dot to E dot square over B, and the map on cohomology, the induced map on cohomology. And then TC, this parametrized TC, is greater than or equal to the couplings of the kernel of this delta star. So this is general kind of statement. But I mean, in this particular case, we show that the couplings of this kernel equals height of the Euler class of this Xi double dot of Euler class of Xi double dot plus 1. Okay, so I mean, its lower bound is exactly the height of the Euler class of Xi double dot plus 1. So this state, the proof is a little bit more technical, so I will not give you full proof. What I will do, I will just roughly explain what's going on here. So, so this diagonal map, in the case of spherical bundle, this diagonal map is a section of a bundle which is shown here. So there's projection on the first vector. Delta goes from the base to the total space x. So, and delta star is induced map by this section, by this delta. So now we can ask a more general question. It's easier to look at more general question. It's easier to consider the following general question. So suppose we have a vector bundle and we have a section of the unit sphere bundle. Okay. And we ask, what is the couplings of the kernel of the map induced by this section on cohomology? And the answer is the following. So we let's look at this section, and then the section defines a perpendicular subbundle. So let's call it F dot. So this is a set of unit vectors which are perpendicular to the section. So a vector E lies in F dot if it is perpendicular to, so you project this vector down and then take section at this point. So if it is perpendicular, then it belongs to this F dot. So this F dot is a sphere bundle of dimension 1 less. So the sphere has dimension q minus 2. And it has Euler class in dimension q minus 1. So this general kind of theorem says that the couplings of the kernel of the map induced by the section equals height of this Euler class of this eta plus 1. And this I will not will describe the proof because it's a little bit technical and I mean, it's in the published paper. So if you apply this statement to our situation, this bundle eta becomes this bundle which we call psi double dot. So now let's consider some examples. So suppose that we have a vector bundle which admits a complex structure. Then for any unit vector, we have this vector which we multiply by square root of -1, which is linearly independent of E over R, they're linearly independent. And then we can orthogonalize it by this formula. So we obtain, for every E, we obtain in a continuous fashion, a vector perpendicular to E, unit vector which is perpendicular to E. So this means that the sectional category of this bundle psi double dot is 0. And we obtain the following corollary, that for any vector bundle admitting a complex structure, TC of this unit vector bundle is just 1.
So this will be just the topological complexity of the fiber.
And it equals cohomological complexity of the fiber, exactly. Because the fiber is odd dimensional, yes. Yes, exactly. As an example, if you take complex line bundle, so it's two-dimensional real bundle, and unit sphere bundle is a principal S1 bundle, so TC equals 1, we know this by before, right? So it's just confirms this case. So now, I mean, this is a theorem which kind of which uses this previous theorem, but it has advantage that we are dealing here with bundles and cohomology classes of the base, because I just want to emphasize here this this psi double dot and its Euler class is in cohomology of E dot, so it's not in the base. It lives in the unit sphere bundle. So it's sometimes it's not so easy to compute its height because it lies in cohomology of E dot. But this theorem, in this theorem, advantage is that we are dealing with cohomology classes of the base. So let's see. So here we make an assumption that our bundle is a sum of something plus trivial line bundle. So, and we will assume that total rank is odd. So the fiber is even dimensional sphere. And then this TC of this unit sphere bundle is greater or equal than height of the Euler class of eta plus 1. And moreover, it is greater than this +2, height of Euler class +2, if this height is even and cohomology of B is two torsion free. So, I mean, this we will see how to apply this example in this case. So we take base CPN and eta to be the canonical rank 2 vector bundle, complex line bundle over CPN. And we look at psi, which is the sum of eta plus epsilon. Am I okay with time? I think I'm okay. So this bundle psi is eta plus epsilon. And Euler class of eta is the generator of H2 of CPN, and its height is n. So we obtain that TC of this unit sphere bundle is greater or equal than n plus 1. And moreover, it is greater or equal than n plus 2 if n is even. And in general, if you use this general upper bound applied to this situation, we get n plus 2. Thus, we see that in this example, for n even, we have TC, parametrized TC equals n plus 2. So we, I mean, this example shows that we can have parametrized TC of spherical bundles arbitrarily large. Okay, oh, this is a corollary. And then there is another corollary which I want to mention here. I mean, all these examples, I mean, you see these examples, interesting examples with high TC is when you have one trivial bundle there. But if you take just eta itself, TC equals 1. So it's very small. But if you take this corollary says that if you have a bundle which has two linearly appended sections, so you have two epsilons there, then TC will be maximum 2. So it's quite interesting that all kind of examples with large parametrized TC, they are of this type when you have one trivial summand. And finally, I want to describe a result where we use estimates using the Stiefel-Whitney classes. So, and here we don't need to assume that the bundle is orientable. So here we introduce this notion, what we call relative height of the Stiefel-Whitney class. So Q is a rank of this vector bundle. So we look at class top Stiefel-Whitney class WQ, and one below is WQ minus 1. So this height of this WQ minus 1 with respect to the top Stiefel-Whitney class WQ. So this is a number, this is an integer. It is the smallest integer, or you can say it is largest integer, such that this case power of WQ minus 1 does not belong to this ideal generated by the top Stiefel-Whitney class. And the main result is that TC is bounded by this relative height plus 1. Okay, well, I just want to emphasize this follows from the main theorem, which I mentioned before. And as an example, we can take, again, so we take eta is a canonical line bundle over RPN, so it is one-dimensional line, real line. And we take k times k eta plus epsilon. So rank Q equals k plus 1. Top Stiefel-Whitney class is 0, and one below is alpha to power k, where alpha is a generator with Z2 coefficients. And combining this, so relative height is integer part of n divided by k. And this upper and lower bounds, they give as an upper bound slightly bigger than lower bound. So they don't match, but the difference is just 1 in this case. So well, all these examples which we looked at, where we used Stiefel-Whitney classes, they don't give the full answer, but this integer Euler class, they give full answer. I think I will finish by just mentioning these 2 references. I think that's it. Thank you. Thank you for your attention.
Thank you very much. Thank you very much for a wonderful talk. Are there any questions?
Well, I have one. Jesus. Oh, go ahead.
I was going to ask if any of your examples are odd. Do you have an example of an odd sphere bundle which is orientable, but its TC is 1? That was my question. I don't know if I missed it.
Oh yeah, I mean, any complex bundle, if you take unit sphere bundle, it will be TC1. Should I show you my slide?
No, I meant, sorry, I meant to ask an opposite question. So do you have an example of an orientable odd sphere bundle where TC is bigger than 1? That's what I meant to ask.
Oh, yeah, of course. Let me just share screen again, sorry. Yes, if you look at this example, so we take CPN and eta is rank 2. This is a complex line bundle, and we take psi is a sum, eta plus epsilon. Okay, so for this psi, TC is n plus 2. So n may be arbitrary, so it can be. So it is oriented bundle. So TC is very large, but it is not complex. It is complex plus epsilon. Mark, is it okay?
Yeah, but I think the fiber is even dimensional then, isn't it? Or are you adding on
Yes,
you're adding on a real line bundle?
Yes, it is even dimensional. So what is your question? Sorry.
Okay, let me try and formulate the question again.
Well,
if you have
the fiber is even dimensional because TC, parametrized TC is greater than TC of the fiber. So it can be 2 or higher. It cannot be 1 for if the fiber is even dimensional.
So my question was, I guess, if you have a odd sphere bundle, which is orientable as a sphere bundle, does the TC equal 1? Or can you produce examples which are perhaps coming from orientable vector bundles where the fiber is an odd sphere, but TC is bigger than 1?
Yes. Yes, I can, but I'm not sure I have it prepared in this in my slides. But yes, I'm sure I can. We can talk later. I can try to answer this question later. What if I stop sharing? Yes, I will try to answer your question, but I don't have it prepared. It's a good question. Thank you, Mark.
Thanks.
Good.
Michael, so when you add on one trivial bundle, you get these big TCs. but when you add on more trivial bundles, the parameterized TC is less than or equal to 2.
Yes, exactly.
And so the question is, how do you interpret that in terms of motion planning?
It's a good question. I don't know, but yes. So I mean, when you have two trivial, two epsilons, you can think of it as a single complex line bundle there, and use it. And using it, you can show that it cannot be greater than 2. I mean, this proof uses this fact that the two trivial bundles together, they form a complex bundle. But yeah, I mean, maybe this is, I cannot answer simply. I mean, there is a lemma which is in the paper. So it is based on this lemma, but I don't have it in my slide. So, so John, maybe I'll try to answer your question also separately.
Okay.
Michael, I have one question.
Yeah.
In your very last example in your slides, so you were considering multiples of the half bundle over real projective spaces plus one trivial bundle, right?
Yes. Yes. Do you want me to show? Let's just.
Yeah, that would help.
Let's see. Let's see. Yes, this one, no? So we take k times eta plus epsilon.
Right. So now, if I remember from my old days as a student, the Tom complex of this bundle is a standard real projective space. So I was wondering, if this is true, then I was wondering whether that might give a sort of interpretation for the conclusion on the bottom of your slide. I have no idea, but it just remembered that this kind of nice fact that the Tom complex of this bundle is a standard real projective space.
Oh.
I think. So I was wondering whether this is related to the conclusion.
Well, this Tom complex is used in the proof of the main theorem, but not in the specific example. So it's, well, it is good. I mean, I'm sorry, I give the same answer. They're all good questions. See, this theorem about the couplings of a section, meaning if we have a section, what is the couplings of the kernel? So the proof of this uses Tom complex associated to this section. You collapse this part of this sphere. You represent the sphere bundle as a union of two disk bundles, and you collapse one of them to a single point, and you get Tom space of this actually bundle, which is denoted by eta here. So this is part of the proof of the theorem. But what you say is very interesting. I don't know if you can use directly. You're saying that you can use this. Are you sorry? Are you saying that you can use? So can you tell me what you mean actually here?
I'm not saying anything. Actually, I was asking, and this is just kind of a hunch, that might be something behind on this type of conclusion if you use the interpretation of this Tom complex, in this case, in this particular case, as a stunted real projective space. But this is just a hunch. I have nothing really interesting to suggest here.
Interesting. Thank you. I'll think about it. I'll think about it. I think there is a question I see here in the chat.
May I ask my question?
Yes,
dear
please.
Michael. Thank you very much for your nice talk. Of course, my question, the good point is that also Professor Gonzalez is here. So this idea of this continuous setting and this parameterized. I know that Professor Gonzalez has this simplicial version of that. By my background from graph theory and simplicial complex, I'm coming from computer science community. So is there any discrete version of this parameterized complexity for simplicial complex cases or graph theoretical setting?
Thank you. Thank you. Very nice question. I know that work of Jesus Gonzalez and also Tanaka related to discrete version or simplicial version of TC, and I consider it very interesting. I think it is a very interesting approach, and in fact, I think that this discrepancy between topological complexity and, let's say, real complexity may potentially lie there. Maybe real complexity is something which you measure by simplicial methods, simplicial, I don't remember your notation, STC or something like that, simplicial TC. It is possible, but you ask me.
I ask it because I see in your examples some common feeling that it is related to complexity of graph. I mean, this related to this cyclotomic number, or let's say Eulerian characteristic, Eulerian characters, Euler character. So that's bothering me that maybe there is some connections.
I cannot tell you anything. I don't know. Maybe, but I cannot answer this question.
Very nice talk. I really searching for this to see those connections, and you are mentioning this real complexity. That's very interesting. Thank you.
Thank you very much. Thank you.
Michael, I have one further question.
Okay, sure.
Let me go back to the case of Fadel-Neuwirth vibrations. And so let me think of non-parametrized TC. And in your work with your collaborators, you showed that if the obstacles are moving in a sort of known way, then that doesn't really matter for the actual answer, because you can somehow deform the space following back the movement. So now in the parametrized, I was wondering whether you would expect some similar situation in the parametrized case where now you allow obstacles to move, and then you have to move in between several of the fibers.
Well, actually, we wanted opposite. We wanted in this paper in this work, we wanted to see that it is this parametrized TC is higher, and we wanted to examine, can it be higher? Because indeed in that paper, which was quite a while ago, I mean, there was obstacles were moving, but robots knew how obstacles are moving. Everything was known in advance, and this didn't create any additional complexity. So this we viewed as a kind of surprising and contradicting some kind of intuition. And I mean, so I don't know, I mean, you ask if we can have the similar situation in this parametrized version. I don't think so, but who knows? But our kind of main emphasis was on opposite, to see that it is different, to see that it is higher. And
Okay, thank you.
Can I ask a question?
Yes, go ahead.
Thanks for a very nice talk, Michael. In if you're looking at modeling robots, so that isn't it better to model them not as points, but points with vectors, because an actual robot has a front and a back.
Yeah.
So for example, if you're navigating a robot on a two sphere and you want to get to an antipodal point, you just say, well, walk directly in the direction that you're facing. Whereas, you know, if you just model it as a point, that doesn't make sense. Has anyone thought about modeling robots with
Yes.
their orientations? Yeah.
Yes. First of all, I totally agree with you that in real life, robots have sizes, and what
Yeah.
we see the idealized version when they have size 0, diameter 0, and it is not exactly what it is in real life. But if we put diameter, I mean, I can say that each robot has a fixed diameter, let's say diameter 1. Then this we have this configuration space and this map, but this map is not a vibration anymore. So the technical problem is that, I mean, of course, we can do the same, this Fadel-Neuwirth vibration. Well, it's not a vibration. It will be a continuous map. So it will have different fibers over different configurations of obstacles. For example, if two obstacles approach too close that a robot cannot pass in between, then they become like a single one. So, I mean, it creates technical difficulties. So this is why we try to avoid this. But in fact, you're right. I mean, it is in real, it should be maybe the next step when yes, when robots have sizes and vibration, the map is
And
not
orientations too. Yeah.
orientations. Yeah. Okay. Yeah, that's right.
Okay. Thank you.
But there are, I know that there are actually many papers when configuration spaces of particles with certain size were studied. Even I know on graphs, I had a PhD student, Kenneth Dealey. He wrote a paper on this. His PhD thesis was, I don't know, like 10 years ago in Durham. And then I know that there are many interesting, more recent papers about configuration spaces of balls within certain boxes and limited. Because if you don't limit them in certain boundaries, then topologically it is the same as you can just magnify. And so yes, it's a very active area of research, and I know that Matthew Kell has many interesting papers with his collaborators, and also Fedor Manin is interesting, and other people.
Thank you.